Welcome to Sundar's lecture. This is lecture number 26, and in the previous class we have concluded the combinational logic circuit, and now we are going to see the new topic, that is sequential circuit, sequential logic circuits, right? So what is the difference between the combinational logic circuit and the sequential logic circuit? I will explain you bit later after completing these topics. What are all the topics we are going to see today, and then I will conclude and I will compare what is the combinational logic circuit as well as the sequential logic circuit. The only difference, that is the only one difference between combinational logic circuit and sequential logic circuit. In combinational logic circuit, if you give any input, that means if you have an AND gate, if you give 0 0, then output will be 0. That's all, simply. What is the output? The output is 0 because the input is 0 0. If you give 1 1 as input, the output will instantly changes to 1, or maybe propagation delays are there, maybe it will change to 1. So the output only depends on the input. That is combinational logic circuit. But if you give feedback of the output to the any of the input, then it will be converted into sequential logic circuit, where you can store a bit or several bits, depends on how many circuits we are building. Depends on that, you can store an element without any storage. You can store. That is what sequential logic circuit. It depends on also the output, right? So right, anyhow, we will see this one. See here, we have taken an NOR gate like this. This is a one NOR gate. This is another NOR gate, and this output is connected to the input of this first NOR gate. Right now, what happens? If you give any input here, the output is also depends on the previous output. The previous output has been given as input here. Like, so anyhow, this circuit is redrawn here like feedback, right? So now what we will do, I will tell you certain terminologies you have to understand before entering into sequential logic circuit. See, we generally say Q last, Q new, like that we will say, or previous state, present state, like that we will say. Maybe we will call it as Q minus, Q plus, which means this is the previous state, this is the present state, right? There are certain terminologies, I may use a different terminologies, but you don't confuse yourself. It will be a previous state and then present state, that's all, right? So anyhow, so this is the circuit now, right? So what happens here, for example, let us assume this previous state is 0, that means it is 0 now, right? This is 0. So if this is 0, I am assuming this to be 0, right? So now what I am going to do, I am going to give this as 0 and this also as 0 now. This is my input. This is my input. Try to understand. This is my input, and this I am assuming it to be 0. So if this is 0, so the present state, maybe I will also call it as present state, next state. Try to understand. Previous state, present state, next state. Everything is same. That means if I say present state, then the other thing is next state. If I say it is a previous state, then the next state will be present state. Anyhow, you try to understand those terminologies, right? So let us assume this is to be a present state output now. This is 0, and what I am going to do, I have given this as 0, this is 0. So this 0 will go here now, right? 0 0. So if both are 0, anyhow, any one input is 0 of an OR gate, the output will become what? 1. You know that it is opposite to OR gate, so this will be 1. Am I right or wrong? So this one will go here now. So if this is 0 1, any one input is 0. So obviously what happens here? So this output 0 1 will give you what? 0 for an OR gate, right? So the next state will be 0. Can you understand what I am saying now? So if the present state is 0 and I am applying R is equal to 0, S is equal to 0, and the next state is also remains 0. That is what we have written here. See here, if S is equal to 0, R is equal to 0, that means the present state, maybe this last, new, anything it may be, right? This is the present state and this is the next state. This is 0 and this is also 0, right? This is the first condition, and let us go for the second one now. Second one. So what I am going to do now, I am going to assume this is 1 now. Present state may be 1, right? What should be the next state? So this one will go here, and if it is 0 1, what should be the output here? This will be 0. This will be 0, right? Because 1 0 of the OR gate is 1, so an OR gate will give you 0. So this 0 will go here. So if this is 0 0, what will be the output of an OR gate? It will be 1 0 0. If you give 0 0 output, then it will be 1, right? So what is the thing here? This is the present state, and this is the next state. See here, present state is 1, next state is also 1. So the thing is, if you give S is equal to 0, R is equal to 0, if the present state is 1, the next state will be also 1. So what is the idea here? This condition, you see, whatever the present state, that will be remain same as the next state if I give S is equal to 0, R is equal to 0. So this condition, we generally call it as no change condition. Can you understand? No change condition, right? So we will go to the next one now, right? Now what we will do, I am going to assume present state to be 0 now, and I am going to give S is equal to 0 and then R is equal to this condition, R is equal to 1, right? This is the condition, and if this is 0, I will write it in red color. If this is 0, this 0 will come here. So if it is 0 0, what happens to the this output? This will become now 1. So this one will go here, and if this is 1 1, what should be the output? 1 1 is out, or gate output is 1, so this will be again 0. But can you understand? So that is the condition here. So if S is equal to 0, R is equal to 0, the present state is 0, the next state will be also 0. The condition, right? Now what I will do, I will change this one now, right? Change this one to, I am taking this to be 1. Present state is 1. Same, S is equal to 0, R is equal to 1 now. So what happens now? This 1 will come here, and if it is 1 0, what will be the output of this one? This NOR gate, it becomes 0. So this 0 will go here. If it is 1 0, the NOR gate output will become what now? Become 0. Can you understand? That is what we have written here. If S is equal to 0, R is equal to 1, then present state is 1, the next state is going to 0. So the idea is, whatever the present state it may be, if you give S is equal to 0, R is equal to 1, then the output will goes to 0. That means this R, which is nothing but it is a reset. Reset, make it to 0. Make it to 0. That is the idea. Try to understand. So this condition, it is a reset condition. Reset condition. What we will do, we will go to the other thing also. So I am going to give now R is equal to 0, S is equal to 1. This is default. I am going to use this condition 1 0. So for that, what we will do, we will take this present state to be 0 now. Present state to be 0, and what happens now? This 0, I will go fast now. This will be now 0. This will come here. The 1 0. The output will become now what? 1. So this become 1 0 means it will be 0, right? So this is 0. This 0 will go here now. If it is both are 0, then what will be the NOR gate output? It will be 1, right? So the next state will become now 1. This is the condition. See here, 1 0. If the present state is 0, the next state is going to 1. And we will change it to now the opposite one. The condition is same. Condition is same. But what we will do, we will assume this to be now 1, right? So this to be 1 now, and this one will come here now. So 1 1, what will be the output of the NOR gate? It becomes 0. This is now 0. So this 0 will go here. If it is 0 0, then what happens to the output? It will be 1. This next state will be 1. See, that is what we have written here. So 1 0, if the present state is 1, the next state will also be 1. So this condition we generally call it as set condition. That is why S here. So when S is equal to 1, the output will be always 1. When R is equal to 1, the output will always be 0. So this condition we generally call it as set. Try to understand, right? So now this one you try to understand, because this is very important thing. So if I am giving R is equal to 1 and also S is equal to 1, let it be like that. So if I am giving if I am assuming the present state to be 0 now, this 0 will come here now. So what should be the output of this one now? So 0 1 means the output becomes here 0. So this 0 will go here now. This 0 will go here now. What happens now? This also will become 0. This output will also become 0. Try to understand this output Q and this is now Q bar. Both the outputs are cannot be same, right? Because if this is 0, this should be 1. If this is 1, this should be 0. And what happens now? Both NOR gates will tend to produce the same output, and which is not possible in this circuit. And also the problem is, which NOR gate has less propagation delay will give the output very fast, and there will be a race condition between these two NOR gates. There will be a race condition between these NOR gates, and no output will be determined. So what we generally do, we always prohibit this condition. This is a not applicable condition, or we can say not applicable condition. Not applicable condition. So we never give S is equal to 1 and R is equal to 1 for a SR latches, right? So this is the basic idea of SR latches, and we will see now different circuit for the SR latches. See here, we have used NOR gates here, and we have used the NAND gates here to build the SR latches. So this is S is equal as R, and same thing. We will get S bar here, R bar here, and if you use this one, so up to this one, if you are using this one, maybe only the NAND gates, and the S bar, R bar, maybe the output will be inverted. One will be the previous state condition or no change condition. 1 0 will be 0, 0 1 will be 1, and 0 0 will be forbidden here for like this. So this will be inverted if you are using a NAND gate. Anyhow, we can also build the circuit like this to produce the same SR latches. If you give 0 0, the output will be no change. If you give 0 1, the output will be if S is equal to 0, then obviously R is equal to 1, then output will be 0. Set reset condition. If S is equal to 1, then it will be set condition. We cannot give S is equal to 1, R is equal to 1. That is not possible in SR latches. So that is what we have simplified this truth table now. So if you give, I am taking this to be the next state. So if you give S is equal to 0, R is equal to 0, and what happens to the next state? It will be the previous state. Same, no change. So this is previous state, right? Can you understand? So no change. So if S is equal to 0, R is equal to 1. So if R is equal to 1, then you can straight away say it is a reset condition. So output will become 0. And S is equal to 1, R is equal to 0. So if S is equal to 1, you can straight away say the output will become 1. That means set condition, right? This is set, this is reset, and you cannot give 1 1. Not applicable. So this is the simplified truth table for the SR latches, right? So this is with NAND gate. That's all, simply. And then see here, This is very important. This is SR latches with enable input now. So what happens here? We will put and this is SR latch. So we generally what we will do, we will put this whole circuit into this one and we will put a box now. We will simply represent it in a box. We never use this diagram again and again, right? So we will generally put a box like this. So if you see any SR like this Q bar, then you have to by default understand the whole circuit is inside this box, right? This is the simple simple diagram to represent the SR latches. And then what we will do now, we will put an AND gate like this, and we are going to give an enable input here. So whatever it may be, if you give 0 here, if enable is 1, then only this 0 will pass through. Try to understand. If enable is 0, then what happens now? The both output will be 0. Enable is 0. If this enable is 0, so on gate one input is 0, the output by default it becomes 0, right? So this will be 0 0. That is what we have given here. So if enable is 0, and whatever the input you are giving, maybe the S is equal to 1, R is equal to 0, whatever you, the output will default will become 0 0. So if S is equal to 0, R is equal to 0, then what is the condition? It is a no change condition. It is a no change condition. And if you give 1 here, you give 1 here, and whatever the value or input you are giving to S and R, it will pass through, and gate will work as a pass through gate. You know those kind of things, right? So what we have done now, we have given an enabled input here. So if you understand this one, we can go for gated SR latches, that is flip flops, right? Gated SR latches, that is flip flops. Maybe we will give pulses, triggering pulses, right? So anyhow, so this is the idea now. So if enable is 1, so the SR latch will work as like what we have seen in the previous slide, right? If enable is 0, then it will act as a no change condition, because S is equal to 0, R is equal to 0, that is the condition, right? Next one, so this is the timing diagram. What we are going to see as a timing diagram, we will try to understand this one now. So enable is high only at this points, and at this points enable is not high, and then you have to understand this one very clearly. This will be no change condition. Maybe I will write it in a different way. S is equal to R is equal to 0 condition, right? That is no change condition at these periods. And enable is 1 now, so SR will latch will look for what is the value of S, what is the input for R, and this is S is equal to 0, R is equal to 0. So this is also no change condition, this is also no change condition. You know these kind of things, right? So what we will do now, we will see only these conditions now. Until this point conditions only we are going to see now. So this one at this point only. So this is also no change condition. Can you understand? This is also no change condition. So I am assuming this to be 0 now. So Q is equal to 0. So no change condition, it will be 0. So at this point, my enable becomes 1 here. So what I am going to do, I am going to see only until this point. Until this point, since at that point only the enable is high. So at this point, R is equal to 0. So R is equal to 0 now, and S is equal to 1. Am I right or wrong? So if S is equal to 1, then what happens now? Output becomes 1 here. S is equal to 1, it is a set condition, output becomes 1. Until this point it will be 1. Until this point it will be 1. And what happens here? Enable becomes 0 here. So until this point, this one, until this one, the output will be 1. There is no change condition, and there is a change here. See here, R becomes 1, S becomes 0, but there is no change in the output. Why? Because the enable is 0. The output has to be the same as what is the previous one. That is 1. So it is retaining at 1 at this point. Try to understand very clearly, right? So at this point, the enable becomes high here. Enable becomes high. So at this point, enable becomes high. So once the enable is high, the SR latch will see for S and R inputs. So what happens here? R is equal to 1 and S is equal to 0 at this point. what it will be now? So R is equal to 1, it is a reset condition. So whatever the output is there, it has to become now 0. It has become 0, right? And at this instant, maybe I will put the instant exactly so that you can easily understand. So this is another instant, because there is a change in the input, and here also there is a change in the input. So you have to see here, and here also you can see here, right? Now you see at this point the R is 1, so the output becomes 0. So it will be 0 because here at all time enable is high, right? So now you see here at this point the set condition yes becomes high, here, right? So as is a high, then the output becomes high until this point, and at this point you see at this point S is also 0, R is also 0. That means S is equal to 0, R is equal to 0. What is the condition? No change condition. So this output will remain same, and at this point the enable becomes 0. So enable becomes 0, then it will be S is equal to 0, R is equal to 0. Condition came to no change condition. So even if R is changing here, S is changing here, the output will not change. It will remains at 1. Try to understand very clearly, right? So for these glitches, maybe the input variation, the output becomes stable as no change condition since S is equal to 0, R is equal to 0, since the enable is 0. So and at this point it will check it out, these 2 points, right? But what happens here, both R and S is 0, both R and S is 0, S is equal to 0, R is equal to 0, then what is that one? No change condition, again the output becomes 1. Try to understand the impact of this enable input shows us that when this enable is high, then only the SR latch will look for SR inputs. Until then, the SR latch will be in no change condition if the enable input is 0. That is the idea we have seen in this timing diagram, right? So this is the symbol of that one, S is equal to SR, and we have an enable here. And what we are going to do now, we are going to see a different one now as a clock pulses now. And you would have understood what is the enable input. Like that, we are going to see the clock pulses now. So what we are going to do, the same diagram what we have seen here, the same diagram, instead of this enable, what we are going to do, we are going to give clock pulses like this, and up and down clock pulses, or like square waves, or maybe rectangular waves, whatever it may be, we will give a clock pulses now. Depends on that clock pulse now, the flip flop, maybe if we are giving clock pulses, then we can say it as clocked SR latches are called as flip flops. We generally name it as flip flops, right? So what is there? These clock pulses, there are different types of clock pulses are available. One is level triggering, one is level triggering, and the second one is edge triggering, right? So what is level triggering and what is edge triggering? See, if the SR latches is seeing S is equal to what is the input and R is equal to what is the input at this particular region, right? At this particular region, we generally say it as positive level triggering, right? Positive level triggering. And if the same SR latch is seeing the S is equal to and then R is equal to values at this instant, only at this instant, means this instant, and whenever there is a positive up is there, then the SR latch will look for what is the input for S and then R. And if it is so, we generally call this as negative level triggering, Can you understand? So there are two things in level triggering. One is positive level triggering and one is the negative level triggering, right? So when SR latch is seeing for S value and not latch, here it is flip flops. SR flip flop is seeing for S value and R value at this point, at this period, then it is a positive level triggering, and this is the negative level triggering. And what is the other thing? This is the first one. And what is the edge triggering now? And why we are going to use edge triggering? It is very simple. If I am going to explain you while we are seeing uh, the flip flop, that means JK flip flop. If you give level triggering, then there is a race conditions will occur. So to avoid the race condition, we will always go for the edge triggering. Maybe you try to understand the edge triggering now, and I will explain you there exactly what is race condition, why we need to use edge triggering for JK flip flops, right? So for example, you have like this now, same thing I am drawing it to explain the edge triggering now. For example, at this positive edge trigger, this is positive edge and this is now negative edge. Try to understand, right? So if at this instant the SR flip flop is looking for S input and then R input, then we will call it as positive edge triggering. Positive edge triggering, right? Can you understand? Can you understand? And it will see at this point, at this point, at this point, at this instant, it will see for S and R inputs, and depends on that it will change the output. That is the idea. That is what we have seen here, right? And the same diagram again, right? Same like this. And if the SR is seeing, flip flop is seeing the input S is equal to what, R is equal to what, at this instant down, the pulse is down at this instant, then we will call this as negative edge triggering. Negative edge triggering. Can you understand this one now? And it will see only at these instances. At this instant it will see, at this instant it will see, at this instant it will see. At this instant it will see what is S, as what is R, and depends on that it will change the output. And it is going to wait until this instant. Until this instant, it won't change the output. It will be remains as what at this instant. And it will see for this instant, and if there is any change in S and R, then it will change the output. Like that, we will have four different triggerings are there. One is maybe major partition is level triggering and edge triggering. And in level triggering, we have positive level triggering and negative level triggering. At this levels, the edge triggering flip flops will not see the input for S is equal to what, R is equal to what. Try to understand, right? That is the idea. Can you understand what is the triggerings are available in the SR flip flops or maybe flip flops? So there are four types. One is positive level triggering, negative level triggering, positive edge triggering, negative edge triggering. That's all. That is what I have written here also. That is what I have written here. So maybe I will look into this one in the next class. That is edge triggered SR flip flops. We will take the example to understand what is this one in the next class, right? So maybe it will be very simple to understand though. Anyhow, I will tell it right here itself. See here, if they have given you like this without any knots here. So if there is a knot here, then it is a negative edge triggered flip flop. They will put like this. They will put like this. If there is like this symbol, this arrow mark symbol, then it is a edge triggered flip flop. Edge triggered flip flop. And if there is a knot here, then this is negative edge triggered flip flop. And if there is no knot here, then it is a positive edge triggered flip flop. That's all. Very simply you can understand like that. Right. Now we have taken here positive edge trigger. Maybe the symbol they will give like this. And if they are giving like this, then this is negative edge trigger. Try to understand. So we have taken here positive edge trigger. So this is positive edge, positive edge, positive edge, positive edge, positive edge. You have like this now. So what it will do now, it will check for this instant only, it will check for this instant only, and this instant it will check, and this instant it will check, and this instant it is going to check. This is the idea, right? So at this instant, see here, we have to see the output here. At this instant, what is the input here? S is equal to 0, R is equal to 0. So I am assuming Q is equal to 0 before that point, right? So it remains in same because S is equal to 0, R is equal to 0. Then what is the output? This is 0 now. So it won't change the output until this point. Try to understand, because there is a clock pulse, rising clock pulse at this instant only. So at this instant, see here, S is equal to 1, that means set is 1. So it is a set condition. So if it is a set condition, the output becomes 1. Output becomes 1. So until this point, the output will remain same. Whatever the change it may happen, whatever the change in SR inputs, the output will not change because it won't see the inputs until the next rising pulse. So it is going to see here at this instant, see here what happens here, the S becomes 0 and R becomes high. So it is a reset condition. The output becomes 0 at this point, and it will hold on to 0 until next rising pulse. Next rising pulse occurring here, and at this point S is becomes 0, sorry, S is becomes 1 and R becomes 0. So it is a set condition, so output becomes 1. So the output becomes 1 here at this point, and until this point it will be hold on to 1. It never going to change the output because the rising clock pulse is occurring at this point, and at this point it is going to see S is equal to 0, S is equal to 0, and R also is equal to 0. What is this one? No change condition. So whatever the output, I am having output as 1 already as a previous state. So the present state will also remains to 0. Sorry, 1. The previous state is 1. So it will hold on to the 1 because there is a no change condition occurring here. And it will see for the next rising clock pulse. Try to understand. At only the rising edges. That is why this is a positive edge triggered flip flop. Positive edge triggered flip flop. So that is what we have written here also. Like forbidden condition, and at a high clock pulse only it will see. So we will conclude now and we will see in the next class. And what are all the topics we have seen in this class? See, I have told you what is the difference between combinational logic circuit and sequential logic circuit. And if you are giving feedback, then we will take it as the sequential logic circuit, right? So we have taken an example, SR latches, and we have seen what are all the conditions are there for SR latches. It is no change, set and reset, set, and the not applicable condition is there. And we have seen another circuit with using NAND gates, and we have seen a simplified truth table for SR latches, and then we have seen enable input SR latches, and we have taken a timing diagram to understand, and also we have seen clocked SR flip flops. Maybe clocked SR latches are called as SR flip flops. And what is the types of triggerings available, and we have seen one by one, and also we have taken an example to understand positive edge triggered SR flip flops, right? So that is what we have seen in this class, and we will see in the next class. Thank you.